Okay, good morning, everyone. So, in the last class, we discussed about adjoint of a bounded linear operator on H. Of course, if you have a bounded linear operator from H1 to H2, where H1 and H2 are two Hilbert spaces, then also you can define T star, which will be from H2 to H1. So we considered the special case where H1 and H2 are same. So then if T is in BH, then T star is in BH. So let T belong to BH and T star be the adjoint of P. Of course, by the definition of adjoint, you can check that there is a unique adjoint. So there is a unique linear operator which satisfies this definition of T star. So we have seen some properties of this adjoint. We have seen that the norm of T star is equal to norm of T and T star star is equal to T. And if we have any alpha T1 plus beta T2 star, this is equal to alpha bar T1 star plus beta bar T2 star. So T going to T star, if we have a complex Hilbert space, that is not a linear map, that is the conjugate linear map. And just a second. And also we have that if we take T1, T2, the adjoint of composition of two maps is T2 star, T1 star. So in fact, more generally, like if you study Banach algebra, then if we have a map on complex Banach algebra which satisfies, so x going to x star, which satisfies these last three properties. So you have x star star is equal to x, and xy star is y star x star, and then you have this conjugate linearity. Then it is called an involution on a Banach algebra. And we have one more very important property that this satisfies. So norm of T star T, if we take, this is equal to just 1 second. Yeah, let me write this norm of T T star. This is equal to norm T square. Of course, in this case, this will also imply that if you take norm of t star t, then by this it will follow that that is equal to norm t star square, and because this satisfies norm of t star equal to norm t, so that is also equal to norm t square. So, but in case of Banach algebra, uh, yeah, so yeah, both of these. So this is norm of t star and norm of t star t equal to norm t square. So let's quickly prove this one. So if you take norm of t star t, so let's start with norm t square. Norm t square. Norm t is equal to supremum of norm tx, where x is such that norm x equal to 1. So we have this square, which is same as supremum of norm tx square, and norm tx square is equal to inner product of tx with tx. And now I can write this as t star tx inner product with x, and this is less than equal to, so in fact we know that this is a non-negative real number, so I can even put mod here. So this is less than equal to supremum norm x less norm x equal to 1, less than equal to 1 or 1, both will give the same thing, of norm of t star t and norm x square, but norm x is equal to 1, so this is equal to norm of t star t. So we got norm of t star t is bigger than equal to norm of t square, and also we know that norm of t star t will be less than equal to norm of t star times norm of t, and because norm of t star is equal to norm of t, so this will be equal to norm t square. So what we got is norm t square is less than equal to norm of t star t, which is less than equal to norm t square. Therefore, they are equal. Norm t square less than equal to norm of t star t. So you see that this is the important one, because the other way we know that this will be less than equal to norm t star times norm t, which is norm t square. So this implies norm of t star t is equal to norm t square. and the other one is because the T star star is T, so we get again this inequality, this equality also. So actually we will not study C star algebra, but this is a property which is very important. So if any Banach algebra satisfies, there is an involution which satisfies this property. If there is an involution, it is called star algebra, and then if it satisfies this, then it is called C star algebra. So, we won't have time to discuss that thing. So, but let's. So we have discussed what is adjoint of bounded linear operator, and so let's write one proposition. Let T belong to B of H, where H is a Hilbert space. Then kernel of T is equal to image of T star, the orthogonal complement of this, and kernel of T star is equal to image T, orthogonal complement. So if you prove one of them, then the other one is because T star star is T, you get this also. So where this kernel of T is all x in H such that Tx equal to 0 and image of T is all T of x where x is in H. This is the standard notation. We write sometime range of T also for this image T. So, so what we have to do? So, suppose we take anything in kernel T. So let x belongs to kernel T. This is equivalent to T of x equal to 0. So x is in kernel T if and only if Tx is equal to 0. And this is if and only if Tx inner product with y is equal to 0 for all y in H. Right? Of course, if Tx is 0, then Tx inner product y is 0. And conversely, if Tx inner product with y is 0 for all y, then you can take y equal to Tx, and that will imply Tx is 0. So these two are also equivalent. Now this can be written as x inner product with T star of y is equal to 0 for all y in H. Now if I take all y in H, then T star y is nothing but image of T star. So this says that x is orthogonal to image of T star. So this is equivalent to x belong to the orthogonal complement of image of T star. Right, so therefore we get kernel of T is image of T star, orthogonal complement, and hence this also implies that kernel of T star will be equal to image of T star star, orthogonal complement, but T star star is T, so that is image of T. Now let's define definition. So T belonging to B of H. H is always for Hilbert space. So T belonging to B of H is said to be self-adjoint or Hermitian operator if T star is equal to T. Like we talk about Hermitian matrix or self-adjoint matrix. Similarly for operator, if T star is equal to T, it is called self-adjoint or Hermitian. And T is normal if T commutes with T star. So T star is equal to T star T. Then T is said to be normal, and T is unitary if T star is T star T equal to identity. So that is same thing as saying that T star is T inverse. So we have defined the self-adjoint, normal, and unitary operator. Okay, so now let me write this. For any T belonging to B of H, T star T is always self-adjoint. So because its adjoint will be equal to T star star, which is same as T star T. So T star T is always self-adjoint, and also any T can be written as any T belonging to B of H can be written as T equal to T1 plus I T2, where T1 and T2 are Hermitian operators. Also, this representation is unique. So this is again easy. So the proof is that you just put T1 equal to T plus T star by 2 and T2 equal to T minus T star by 2i. So then T1 and T2 are both Hermitian, and T is equal to T1 plus IT2. So we get this. And uniqueness again, because if you take any T which is of the form T1 plus IT2, then we have that T star will be equal to T1 star minus IT2 star, but T1 and T2 are Hermitian, so that is equal to T1 minus IT2, and then by adding you will get that T1 is equal to T plus T star by 2, and then by subtracting you get T2 equal to T minus T star by 2i. So therefore if it can be written like this, it has to be unique. T1 and T2 are Hermitian, and T is equal to T1 plus IT2. For uniqueness, T equal to T1 plus IT2 implies that T star will be equal to T1 minus IT2, because T1 and T2 are Hermitian, and this implies that T1 is equal to T plus T star by 2 and T2 equal to T minus T star by 2i. So maybe let's see an example. Let's take T from L2 to L2 given by T of x1, x2, so on, equal to 0, x1, x2, so on. So on the L2 space, sequence space, we define this. This is called the right shift operator. Because we shift the whole sequence to the right by one place. So we put 0 in the first component and then repeat this sequence. So this is right shift operator. Now let's calculate what is its adjoint. I mean, this is a bounded linear operator on L2, because norm of T of x is same as norm of x. So this is a bounded linear operator with norm 1. T belong to BL2 and norm T is equal to 1. So to find T star, we just see if we take T star x inner product with y, then this is equal to x inner product with T of y, and this is equal to, so on the first we have x1, x2, and so on, this sequence inner product with T of y is 0, y1, y2, and so on. And the inner product on L2 is defined as this is equal to summation of xi yi bar. So we get x1 times 0, and then x2 times y1 bar, and so on. So this is equal to x2 y1 bar plus x3 y2 bar, and so on. So this is nothing but the inner product of x2, x3, and so on with y1, y2, right? So t star x inner product with y is equal to this inner product with y, and this is true for every y. So this implies that t star of x1, x2, this is equal to x2, x3, so on. So the adjoint of right shift operator is the left shift operator. T star, this is the T star is the left shift operator. And so in this case, it is not self adjoint. T and T star are not the same operator. And what is in this case, what is T star T? So if you take any x, then T shifts it to the right. So you get 0, x1, x2, and so on. And then T star shifts it to the left. So that again gives you x1, x2, and so on. So T star T, this is just the identity operator, that T star T is equal to identity. But if you take T star, this is not the identity operator, because T star, what it does is, so if you take T star of any x1, x2, and so on, then T star maps it to x2, x3, and so on, and then T maps it to 0, x2, x3, and so on. T star T, the first component will always be 0. So x1, x2, this is mapped to 0, x2, x3, and so on. So maybe one more example, let me write. For any continuous function on 01, C01, define T phi from L201 to L201. Yes, this is the multiplication operator. So T phi of any f in L2 at T is equal to phi of T times f of T for T into 01. So what is T star? So just check that. The adjoint of this T phi is equal to T phi bar. So the adjoint of multiplication operator by phi is the multiplication operator by phi bar. So therefore this T phi is self-adjoint if phi is real valued. Right. So if phi takes only real values, then phi bar is equal to phi. So then in that case, T phi star is equal to T phi itself. So it will be self-adjoint operator if and only if, in fact, this phi is a real valued function. Maybe one more, the projection operator. So if we have M any closed subspace of a Hilbert space H, and let Pm be the orthogonal projection onto M. This we discussed before, that for any closed subspace, there is, for every element y in H, there is a unique element in M, which is at the smallest distance to y, and that defines a linear map from H to M. So this is Pm is a map from H onto M. So it is from it is the bounded linear operator on the Hilbert space H. So what can we say about this? Then this Pm is a self-adjoint operator. And also this projection operator, it satisfies Pm square equal to Pm. So it is such an operator is called idempotent if its square is itself. So it is an idempotent self-adjoint operator is Pm. So
Sir, won't any arbitrary projection operator be always idempotent?
yeah, that is also true. Right. So if I take any projection operator, then that is always idempotent.
But for closed subspace, we were able to define this orthogonal projection.
Yeah, that is true.
Okay.
So this again. So why is this self-adjoint? So let's see why it is self-adjoint. So if I take any x inner product with Pm of y, Or let me write the other way. So we write PM X inner product with Y. This is equal to X inner product with PM star Y. So we have to see that that is same as X inner product with PM of Y. So why is that? So
Like we can probably first express y as pmy plus I minus pmy, and
exactly. So
then
this I'll
PM.
write as the PM of X inner product with the PM Y plus Y minus PMY. Right now, this is equal to PMX inner product with PMY plus PMX inner product with Y minus PMY. Now what we know is that PM of X, this belongs to M, and we know that Y minus PMY, it is in the orthogonal complement M per, right? So therefore this inner product is 0. So this will be equal to PMX with PMY. And again you can write PM X. So yeah, so again if I write this as PMX minus X plus X, then PMX minus X, that inner product with PMY will always will again be 0. So therefore we get this, right? So maybe I'll write here similarly X inner product with PMY. This is also equal to PMX inner product with PMY. So here you express X as X minus PMX plus PMX. So you will get this. So this shows that PMX inner product Y is X inner product with PMY for all X and Y. So that means that PM star is equal to PM. We also have this that if we have any Hilbert space, so let H be a Hilbert space and let P belonging to B of H be a D such that P square equal to P and the P equal to P star. So we are assuming that P is self-adjoint and P is idempotent. So then if we take M is equal to the image of P, this is a closed subspace of H and P is nothing but PM. P is the orthogonal projection onto this M. So the previous example says that if we have any orthogonal projection, then it is self-adjoint and idempotent. here we are saying that if you have any operator on a Hilbert space which is self-adjoint and idempotent, then it is the orthogonal projection operator only. So this thing characterizes the orthogonal projections on Hilbert space. So since we have p square equal to p, x minus px, if we look at, this belongs to kernel of p for every x in H, right? Because if you take p of this, that will be equal to p of x minus p square x, but p and p square are same, so that will be equal to 0. So x minus px is in the kernel of p. So now any x can be written as x minus px plus p of x. So this belongs to kernel of p plus image of p. So this shows that we have this decomposition that any vector can be written as a vector in kernel plus a vector in image. So therefore we have that the Hilbert space can be decomposed as sum of kernel of p and image of p. Also, we have seen before that this for any operator, kernel of t is equal to image of t star orthogonal complement. So that if we apply to this p, kernel of p is equal to image of p star orthogonal complement. But p star is assumed to be equal to p. So this is equal to image of p orthogonal complement. So what this says that image of p and kernel of p are orthogonal to each other. So therefore, we have that this H can be written as the direct sum of kernel P and image P, where these two are orthogonal. Right? So, so therefore, we have that this will imply that image P is also closed, because this is orthogonal complement of a subspace, and this P is equal to Pm. Therefore, H is the orthogonal direct sum of kernel P and image P. And so this will imply that this image P is closed, and P is equal to P of M.
So how do we get that image P is also closed?
Uh, so this is because image P is nothing but the orthogonal complement of kernel of P, right?
Oh, okay. So orthogonal complements are always
Yeah, that is always a closed subspace, right? So therefore we get that this is closed, and because of this that this kernel P is orthogonal to image P. If you calculate P of M, that will be same as P. Right, because that you get PM of X is the unique vector such that X minus PMX belongs to its orthogonal complement. But here you know that X minus the P of X, this belongs to the orthogonal complement, because orthogonal complement is kernel. So therefore this P equal to PM is also true. Okay, let me prove one result for normal operator. Let H be a Hilbert space. And T belong to B of H. So then we have T is normal if and only if norm of Tx is equal to norm of T star x for every x in H. And B is if T is normal, then norm of T to the N is equal to norm T to the N for every natural number N. And also kernel of T is same as kernel of T star, which is image of T orthogonal complement and image of T star orthogonal complement. So in fact, by A, you see that T is normal if and only if norm Tx is equal to norm T star x. So if T is normal, then Tx equal to 0 is equivalent to T star x equal to 0. So kernel of T will be equal to kernel of T star. And kernel of T we know is equal to image of T star orthogonal complement. And kernel of T star is equal to image of T orthogonal complement, but kernel of T and kernel of T star are same, so therefore these spaces are same. This is one important thing, that the norm of T to the N will be equal to norm T to the N if T is normal. We know that this is less than equal to norm T to the N. Now this is true for any operator, but if it is normal, then these are equal. So the first part is easy to prove. So let's look at norm T x square minus norm T star x square. This is Tx with Tx minus inner product of T star x with T star x. And then this can be written as T star T x inner product with x minus this will become T star x inner product x. So this is nothing but T star T minus T star x inner product with x. So now if T is normal, then T star T is T star. So right hand side is 0, therefore norm t x square is equal to norm t star x square. So therefore norm tx equal to norm t star x. And if norm tx is equal to norm t star x, then left hand side is 0, but that will imply that this is equal to 0. So let's write. So t normal implies t star t minus t star of x is equal to 0 for all x, and this implies that norm tx square minus norm t star x square is 0, which implies norm of tx equal to norm t star x. Conversely, if norm of tx is equal to norm t star x for all x, then t star t minus t star x with x, this is equal to 0 for all x, and this implies that this t star t minus t star, this is equal to the 0 operator. So that will say that t is normal. So why is that? So here, in fact, we assume that this is Hilbert space over complex field. So let me write this. This is a complex Hilbert space. And T belonging to BH, then this. So for this, if we have any, in fact, inner product space, so if V is a complex inner product space, and T is a linear operator on V, is such that Tx inner product with x is equal to 0 for all x in V, then T must be 0 operator. So we are using this result. So first of all, you note that this is not true if we take real inner product space. I'll write a remark here. This result is not true real okay. Can anyone tell an example? where you have Tx inner product x is 0 for all x, but T is not 0 operator. So on R2, you take the rotation operator, right? So rotation by 90°. Take P. Rotation. Right. So then for any x in, so on, let's say on R2. So that means that Tx is always orthogonal to x, right? So Tx inner product x will be equal to 0, but T is clearly not the 0 operator, right? So this is not true, but if it is complex inner product space, then this is true. And why is that? So for that, we have this, it follows from the polarization identity. So to prove this, use the polarization identity. To get, if I write 4 times Tx inner product with y, that is equal to T of x plus y inner product with x plus y minus T of x minus y inner product with x minus y plus iota times Tx plus Iy inner product with x plus Iy minus iota times Tx minus Iy inner product with x minus Iy. And now if Txx, this inner product is 0 for every x, then all these 4 terms on the right hand side are equal to 0, and therefore we will get that Tx with y is equal to 0 for all x and y, and that will imply that Tx has to be 0. So that will give you T equal to 0. So this you can check that from polarization identity you can prove this, and then you can get this. So, okay, so now let's try to do B part. So if T is normal, by part A, kernel of T is kernel of T star, and therefore we get that equality. Image of T perp is equal to, एक minute. So this is the kernel of T star and image of T star perp. This is kernel of T. So therefore we will get this. And the other one I'll prove next time because I'm running out of time. So we'll prove this one that norm of T to the n is equal to norm T to the n for normal operator. So I'll stop here. Tomorrow, as you must be knowing, there is no class because there are this project presentation scheduled tomorrow. So we will meet next on Tuesday.